Hello, once again, I'm John Joshua Bilonia, here today to perform the summative assessment for or the application for the servo motor using the PIC. So, for this project, we'll go ahead and create a new one using the standalone project with an optional. Okay, so let's select here PIC 16F1508. And then next, we'll leave it as is since this is just an optional one. And we'll select XC8 as the compiler. And then we'll browse to a folder named SA4. And then we'll name the project as SAX4. Then we'll click on finish. So now that we have the new project now named SAX4, we'll go ahead and activate the MCC. We'll select classic and finish. Okay. Under the system module, let's leave here at the internal oscillator, and then we'll select 2 megahertz, and we'll just leave the low voltage programming enabled. Under interrupt module, there's nothing to change, and for the pin, we're gonna be viewing the pin here. We'll be enabling first under the services here, we'll add resources. First, we'll add a PWM. This is to have a PWM output, and then a timer for the PWM to based on. And in addition to that, we will be adding a DC. So we'll be adding here the ADC. Okay, so it is time for me to explain this project. So this project aims to have a potentiometer be served as a joystick to control the steering of a remote controlled toy car, with the steering direction of the wheels of the toy car being controlled by the servo motor. So this potentiometer will input analog signal to the PIC, which then sends a signal to the servo motor over on the toy car to determine which direction it should steer to. So for this project, I have ordered a ASK receiver and transmitter, or amplitude shift keying transmitter and receiver. But unfortunately, the ASK receiver and transmitter are not quite compatible with the PIC that I have. So for this experiment, we'll just have the servo motor directly connected physically to our PIC instead of connecting it to a ASK receiver. So unfortunately, though, the receiver and transmitter of ASK signals cannot be used. So for this, we'll be first customizing our timer here. We'll of course enable it and set the prescaler to 1:64, and then we'll type in 20 milliseconds, which in the actual period has 19.968 milliseconds. So under the PWM, we will now have to enable the pin output of the PWM. So this will be the output here will go through the servo motor as the controlling signal. So the duty cycle still have here and active high. So as you can see here, the PWM frequency is now near 50 Hertz, which is the operating frequency of the SG90 servo motor which I have. Okay, so for the ADC, we'll just have the result alignment to right, the positive reference to VDD, and no auto triggering. And after that, we can now go to our grid view of our pins and enable the ADC input to be at port RA2. So we'll disable this. So port RA2 will now have our potentiometer input. And then we have here our PWM output is at port RC1. So going to our pin module, we can change our potentiometer name to just pot. So it would be a potentiometer. Of course, it's an analog input. It's not an output. While our RC1 would be a digital output. So let's just uncheck analog for digital, and then let's uncheck the output. So the potentiometer will be an input. So after that, checking. Now that all is done, we can now generate our code. So generating. So we can now see here our generation complete message. So we'll access now here our source file. Under the source file, we'll access our main file. So here on our main file, let's first have here the ADC be initialized. Initialize, so that the ADC will be starting to convert the position of the potentiometer every cycle of the scan. So after initializing the ADC, we will now declare a unsigned integer or uint16. So that stands for just unsigned integer, which is 16 bits. So this variable will be named as position. This position, of course, is obviously or just pos for short. This pos or position is of course the result of our ADC get conversion. So this get conversion, of course, from our pot, very important there. So this function gets the converted input from our potentiometer, which then assigns it to the variable position. So we'll have here pos is potentiometer position. We can just have it at the next line. So next, we will want to have the potentiometer input be converted to the to a number that the servo motor recognizes, and that is to say that the servo motor only recognizes unsigned 16-bit inputs. So we have here the potentiometer position be also an unsigned 16-bit integer. So with that in mind, let me create here outside the while the main code will define here a function. So we'll define a function, let's say uint16t, because it only recognizes uint16 or unsigned 16 bits, and then we'll declare the function as map, which has arguments of let's say value. So of course we'll have to declare it as an integer. So that is the first argument. The second argument would be input minimum, and then the third argument, which would be also an integer, is input maximum, and then our fourth one would be integer, which it stands out for the output minimum, and then of course our output maximum. Okay, so in min, of course, let's have here, and then in min is, oh, of course, it's already self-explanatory, so we'll have no comment. So in min is just the minimum input, the in max is the maximum of the input, which is our input would be the potentiometer, of course. The out min would be the output minimum, the out max would be the maximum output, and our output, of course, would be the signal control for our servo motor. So for thinking of it logically, we will have to convert from the position of the potentiometer to the 16-bit unsigned integer that could be recognized by the servo motor. So by logic, we can deduce that we'll just have to have a ratio and proportion equation here, or expression. So we'll have here that the function should return, theoretically, a value that is equivalent to, first, the position of the potentiometer. So to have that is this value here would be the position of the potentiometer. So we'll have value, and then we'll subtract the minimum position, which is the input minimum, which is in min, so that we can assure that this ratio and proportions will be very accurate. So after that, we have the offset of our potentiometer. That's the offset value of our potentiometer. Of course, we'll multiply it by a value that is the whole range of our potentiometer input. So the whole range of our potentiometer input would be equivalent to the input maximum minus the input minimum. Oh, however, since we're converting from the potentiometer to the servo motor, this function should return a value that is recognizable by the output. So this should be multiplied by the output range. So the output range would be just output max, or out max, minus out min. And then this quantity would be divided by the quantity of course, the input range. So the input range would now be in min minus in max, of course, in max minus in min. Okay, so this is one whole quantity, and of course we'll just add the minimum output so that we can simulate the offset of the potentiometer here. So this just simulates the offset of the potentiometer. So the servo would just follow the movement of the potentiometer in proportional rates. So it would have the same angular velocity, and it would also have the same position as the potentiometer knob. Okay, so having that in mind, so we'll just close out this quantity, and of course a semicolon here. Okay, since now we have our value converted from the input to the output, we can now have another assignment here, which would be accessed by the duty value for the PWM. So first, we'll create and declare an unsigned bit, an unsigned 16-bit integer as usual, named map. So this map is the value that should be revealed by this function. So the variable map is equal to the function map, of course, where the first argument is value or the position. The position is pos. So the first argument would be pos, and then the second variable here would be input minimum. Our input minimum is of course 0 because the potentiometer is a 16-bit is also a 1024 valued range. So that would be 0 to 1023. So for the third argument, we have here in max. So in max would be, of course, 1023. And then we have here the output minimum, which will just set to 0. And then the output maximum will just be setting that to 90. Because as observed from previous attempts, the servo motor SG90 can have its pulse width have the value of 90, and it will be corresponding to a slightly greater than 90-degree angle. Okay, so now that we have that, of course, after mapping it to the value map, we'll just have to access the PWM. And of course, our PWM is 4. And then we're just gonna load its duty value as the value of this variable here. So this variable is named map. And then, of course, we'll introduce a delay in milliseconds of 19.968, which is the exact period as determined by timer 4 here. So the actual period here is 19.968. So that's why we're putting 19.968 here, just to be precise. Okay, so before we have this function here, it should be declared first here after the inclusion of the generated files, so that it can be accessed later on in the code. So now we can now build our code. So building it, so we have many warnings because of the implicit conversion from integer to unsigned integer. So if you can see here, we have the warnings for implicit conversion uses integer precision from unsigned into unsigned character, and so on and so forth. But in the end, it still would be converted to unsigned integer 16 bits. So now that we have our build successful, we can now go ahead to our IP here, where we'll be loading our hex file. Our hex file is under here in the folder SA4, where SA4 distribution, of course, the default production, and we have here the production hex. So that we have our hex file loaded successfully. Since we have already connected our PicKit tree here, we can now program our PicKit tree. So programming it now. So programming is now complete. We will now disconnect it and go over to our circuit. But before we move on, I would like to change something in the code here. Instead of going the full potentiometer, we'll just be using only half of the potentiometer, because our servo motor cannot turn full 360, while our potentiometer can go over 270 degrees. So we'll just be using half of only of our potentiometer. So we're just gonna be building it. So build is successful. So we'll just reload our hex file here as automatically done by the IPE, and of course program it. So now that our programming is now complete, we can now go over to our circuit. Okay, so going over here, so never mind this is just our power supply. It has just many adapters. So this here is our potentiometer. It's a 50 kilo ohm potentiometer, as you can barely see yan. 50k potentiometer, 50k ohm potentiometer. And this here is our SG90 servo motor. Yeah, and then we have here, of course, our PIC 16F1508, and then that's all. So first, on our PIC 16F here, first we'll have the pin number 1 here. This pin number 1 should be connected to the power supply. Okay, the power supply. And the power supply would be going to the other part here, to this part of the board. Can't be seen. Okay, so that's our power supply. So for negative supply, so here we'll be accessing the 20th pin, or the last pin here, and then we'll be having it on the other side of the breadboard. And then after that, we'll be having our servo motor input, or what should we say this? This would be for the data of the data signal controlling the servo motor. So for this, we'll be putting here at RC1, which is actually here 1 2 3 4. Skip here, and then we'll have it right here, port RC1. And then after that, we now have our potentiometer input in red, and our potentiometer input will be put at RA2, which is right here. Potentiometer input is at RA2. So RA0, RA1, RA2. So RA2 is here. So now we have both our potentiometer and servo motor inputs. Will be connecting the power supplies for the servo motor and the references for the potentiometer. So first would be the references for the potentiometer, where black would be connected to our ground here. So we'll be connecting it here. Let's move it here. And of course, the white one would be going to our supply here. At the other side. Same goes for our servo motor, where our servo motor ground will be presented in brown. So this of course goes in here, and in the other side would be the servo motor supply, which should be in red. So here, okay, and then we'll be connecting it to the servo motor now. So for the servo motor, we'll connect the red to the red wire also, the red to the red wire also. So we'll be connecting that to the red wire. And this brown would be connected to the brown wire also, which is the ground. And this yellow line here, which carries the data, would be connected here to the green. Right, can be seen here. So we can now connect it here. Okay, so now that the servo motor is now connected, we can now connect also our potentiometer. So wait, okay, our potentiometer would be here, where this would be the supply, the positive reference, and this would be the negative reference. The negative reference is the negative reference would be the one with the metal thing protruding here. So getting it on, so the black portion connects here, the white portion connects here, and the input would be, of course, by red from RA2 to here. Okay, now connecting our supplies. We'll be connecting first the -1 and then the positive supply. Okay, so wait a second. Okay, so here I have in my hands our servo motor, which would be inverted in our view, and our potentiometer, which would serve for the joystick of our remote controlled toy car. So for this project, again, is aimed at an implementation for the remote controlled toy car, with the potentiometer as our joystick or steering wheel, the steering direction, and our servo motor as the one controlling our the direction of the front wheels of the remote controlled toy car. As said earlier, it is unfortunate that the ASK transmitter and receiver are not compatible with this setup, but I've tried my best to have it work, but it really didn't work together. So as you can see now, so first, so as you can see, it's hard to see the blade of the servo motor. Wait. Okay, so as you can see here, if I twist it to the right, it would also go to the right, and vice versa. So the speed at which I turn the potentiometer knob is also the speed at which the servo motor responds, albeit with only a short delay, with a very minimal delay, I guess about 100 milliseconds delay, but still it has a very fast response. As you can see, I only use half of the potentiometer so that it would not overwork the servo motor. So if I stop, it also stops. Okay, so that's it for the project application of the servo motor and the PIC, together with the analog input of the potentiometer as a control for the steering of a remote controlled toy car. So that is all. Thank you.